Hello, welcome to PhyzQuest. So this is the solution video for GATE 2020 Physics question number 8. The question is, a particle X is produced in the process pion plus proton giving kaon plus X via the strong interaction. So if the quark content of the kaon is given as US bar, the quark content of the X we need to find out. So let's get started. So this question comes from the section Nuclear and Particle Physics, and the concept involved here is particle decay. So here we have a decay process is given, and the question is we need to find out the quark content of a certain particle. So here we can approach the problem in two ways. First approach would be to identify the particle and then find out its quark content. So this is the decay process, pion plus proton giving kaon plus X, and we need to find out the quark content of X. So first approach is to identify this particle, and from that we have to find out the quark content. Once we identify the particle, then we know how to get the quark content of that. So now in order to identify the particle, what we have to do is we have to use the conservation law. There are a certain set of conservation law which every decay process should follow to have a valid process. So applying that law, we can get the profile of the particle X, and from that profile we can find out what could be the particle. So here first law would be the conservation of charge. So when we check the charge, so here it is pi plus, so it has a charge +1. Proton also have a charge +1. Similarly, kaon, it has also given it k plus, so it has also a charge +1. Now in order to have a charge conservation process, so here we have 1 + 1 2, and here also you have 1. So in order to have a valid charge conservation, this X would also have a charge +1. So therefore charge of X is equal to +1. Next conservation law is conservation of spin. So here pion is a spin 0, proton have spin half, kaon have spin 0. Again, to have a conservation of spin, in this case X would have a spin as half. So spin of X is equal to half. Third is conservation of baryon number. Now here pion is having baryon number 0. Proton is a baryon, so it has baryon number +1. Kaon have a baryon number 0. So again, to have a conservation of baryon number in this case, X should also have a baryon number +1. So that means baryon number +1 means X is a baryon. That means baryon means X can either be a nucleon, that is neutron or proton, or a hyperon. So depending on, it can be lambda or sigma or cascade or omega hyperon. It can be anything, either a nucleon or a hyperon. So we have got a set of particle, from that we can choose. Now, but we still don't know what is exactly the particle is. Now next move ahead with another conservation. So here it is already mentioned in the question that it is a strong interaction. So strong interaction means there is another conservation law has to be applied, that is conservation of strangeness. Now for pion the strangeness is 0. For proton also have a strangeness 0. But in case of kaon is a strange part, have a strangeness which is +1. So from left hand side the total strangeness is 0 + 0, which is 0. But on right hand side we have one particle have a strangeness +1. So X, in order to have a strangeness conservation, X would have a strangeness -1. So now here strangeness is -1. Now since the particle is having a strangeness, that means it cannot be a nucleon, because nucleons are not strange particles. So it's definitely a hyperon. So now we have got a profile of the particle X, that is its charge is +1, spin is half, then baryon number is +1, that means it is either a nucleon or a hyperon, and the strangeness is -1, so that means it is definitely a hyperon. So now all this profile is, if you look at a list of this hyperon, you can see that all of them having charge +1 is only this one, that is sigma plus. So particle X is sigma plus. Now we have got the particle, so its quark content is UUS, that is the quark content of sigma plus. So this is one approach. Now let's move ahead with the second approach. Second approach is directly getting the quark content without identifying the particle. Now it can be served as a shortcut method. So it is already mentioned that it is the decay process is a strong interaction. So that means for strong interaction the total quark content has to be conserved. So which means the total quark content on the left hand side should be same as the total quark content on the right hand side. So now this is our reaction, the decay process. So pion is a meson. So that means meson have a quark and anti-quark combination. So it has the quark content as UD bar. Again, now proton. Proton is a baryon. So they have a quark content that is a combination of 3 quarks, and proton will have a combination UUD. So the total quark content on left hand side will be D and D bar will cancel each other. So total quark content on left hand side will be UUU. So now in order to have a valid strong interaction, right hand side will also have a total quark content UUU. Now it is given in the question that for kaon the quark content is US bar. Now here you can see that it is mentioning as S or S bar. They represent a strangeness. Now again, a strong particle in a strong interaction, the strangeness has to be conserved. So in the left hand side, both the particles are not strange particles, but in right hand side we have one strange particle which is having the strangeness -1. So in order to have strangeness conservation or to balance the strangeness, X should have a term S. So it can balance the S with S bar. So one of the quark content has to be S, and again the total quark content again has to be conserved. So already we have one U here in kaon quark content. So that means the rest of the 2U has to be from X. So the quark content of X will be UUS. So the quark content we have got as of X is UUS. So now let's check the option. Now you can see that option C is matching with our result. So correct answer for this question is option C.